A little gem I found in this book again. I'll read it out to you. Page 64. But it would be a mistake to conclude that the abundance of various elements on the Sun is given by the relative intensity of the corresponding Fraunhofer lines, which are absorption lines, the little black lines you see in a spectrum, in other words. So you have your emission spectrum, which is the bright lines that show up, and then you have your absorption spectrum, which has the entire band with little black lines in the middle, and those are the Fraunhofer lines. I guess it was in vogue in the 1960s to call them Fraunhofer lines instead of absorption lines. In fact, the intensity of absorption of various atoms depends on the high degree and the physical conditions to which they are subjected. Take, for example, neon atoms. If we shine white light through a glass tube containing neon, and we look at it through a spectroscope, we will see a continuous spectrum without any absorption lines whatsoever. On the other hand, neon gas becomes luminous and emits bright red light if an electric discharge is passed through it, as is done in neon advertising signs. Does it contradict Kirchhoff's law? Not at all. In the first case, all neon atoms remain in a normal state of lowest energy, and the energy of the white light quanta does not suffice to raise the electrons from this state to a higher state. Thus, no quanta of the light passing through are absorbed, and no dark lines appear in the spectrum. However, when a high-tension discharge is sent through a neon-filled tube, the electrons rushing through the tube possess enough energy in collisions with the neon atoms to excite them and to lift atomic electrons to the higher energy levels. In returning to the ground state, the excited electrons in the neon atoms emit the light quanta, producing a bright red line characteristic of neon in the spectroscope. And if we shine through a luminous neon tube white light of high intensity, we shall see in the spectroscope a bright continuous background with a dark line at the place where the red emission line of neon was, just exactly as Kirchhoff's law says. And basically, I don't want to read the rest of that, but the main point was that he basically just overviewed why the sun's shining. It's plasma recombination. You have the excited ionized neon or hydrogen or iron or oxygen, and when it goes down to a lower energy state, it emits a quanta of light, and that's why the sun is energetic. It says here, this is exactly what happens in the sun's chromosphere. There you go. It's plasma recombination. And what I really find disappointing is that feedback loop between the recombination of moving back to a lower energy state, emitting light, and then being re-ionized because of the sun's turbulent atmosphere is why the sun is, hot and bright to begin with. It literally, it's the sun's turbulent surface. This is the chapter, page 63. It's really incredible how he just goes out and says it. And it's a basic phase transition too. Remember the little graph I did this with a little marker, but you have your plasma moving down and becoming gas, and then the gas moves down and become solid material, and gas becomes liquid material, and these two go back and forth over time. As well, the feedback loop can go up here, down here, up down there, up there, and then it can continue. This is where hot, bright stars are, that's where their phases are. That's where their phase transitions are, so to speak. But when you go to Wikipedia, and yes, I suggest going to Wikipedia and looking for this understanding, you'll find that nowhere in either the stellar evolution page or the nebular hypothesis, which is redirected from the planet formation page, has anything to do with a basic phase transition called plasma recombination, even though everybody knows that's exactly what happens in the surface of the sun. It's like they're talking of the weather, yet they don't mention the rain or the wind or the sun heating the surface of the earth or tornadoes or hail, or they don't. It's like they completely ignore what it is they're supposed to be talking about. That's what it feels like to me. And 1964 they knew about this, so it's been over 50 years, and they still have yet to come to the terms that a hot, bright star like the sun will remain hot and bright until all the plasma has recombined into gas and it becomes what's called a brown dwarf, which then the gas obviously becomes solid and liquid material. It's as simple as that, people. But these astrophysicists are they're so absorbed in what they were learning in school that they completely gloss over like the most obvious understandings. I just thought I'd share that with you guys. And as well, this book has a really good table. I can actually get a lot of information from this, believe it or not. It says here, the ionization potentials of some abundant elements. And the number, the Roman numeral of it is a degree of ionization. And if you can see that, hopefully you guys can see that, but there it is. You know, you have potassium in here, argon, silicon, aluminum, magnesium, sodium, neon, oxygen, nitrogen, carbon, cobalt, nickel, strontium, chromium, vanadium, titanium. And you literally can look at the degree of ionization of some of these elements, and mind you, the differentiation process itself as the star evolves will have the lower degree of ionization material collecting in the center first and forming molecules first. That's why iron is the center, cobalt, nickel, and the degree of ionization, when it gets really energetic, those are the ones that are in the high atmosphere, such as, you know, carbon, nitrogen, oxygen, neon, sodium, aluminum, silicon. That's why those are in the crust. When the star is differentiating itself, it differentiates based off of the ionization potentials of the material. Similar to, you know, Markland convection. Markland convection is a very advanced concept that I have yet to completely understand, but I think that's laying into the basis of Markland convection, is sorting the material based off its ionization energies rather than its mass. So to look at a lot of astronomers and astrophysicists and how they differentiate stars, they say, oh, the heavier elements fall to the center first. No, it's incorrect. We know that the material that has specific ionization energies are the ones that cool the first, and then they collect in the center first, regardless of how heavy they are, because, as we all know, electromagnetic forcing is much more dominant when the material is ionized than gravitational forces. And that should be something that should be taught in school, but apparently it's not. And I'm just going over this and looking at the volumes and percentages of the sun, looking at a lot of the really old school diagrams in here concerning, you know, the Doppler effect of a lot of the turbulent material and things like that. But I just wanted to share that with you guys because it's not supposed to be that difficult to understand stars. But astronomers these days, they've forcibly made it difficult, I guess, to employ more people so they can talk about more things and more theoretical stuff that, you know, everybody has to spend years and years and years on trying to understand. But it's quite literally a waste of time. You should be able to focus yourself on concepts that are realistic. But today is August 3rd, 2015. Everybody have a good day.